Similarly, let us draw the horizontal loading diagram. Okay. So, taking moment about B. So, A, this is C, this is B, this is D. Taking moment about from here to here, I think it is 600. This is 1100. This is 500. Here it is 400. Okay. Now, taking moment about B. Now, okay, of course, before that, you must know the sign convention here because we are drawing the horizontal loading diagram. When I draw the horizontal loading diagram, I have to look from the top. Now, looking from the top towards my right, we'll take it as positive. Please see here. Towards my right, positive. That is, say, call it as upper. Say, because when I draw the loading diagram, okay, I cannot show it in that direction because it is not, because we are writing on the board. Okay, so we will use some convention here. Towards right means up, towards left means negative. Okay, minus, down. Now let us call it as down. Okay, so this is the sign convention. I hope you understood. As viewed from the right hand bearing, looking from the top, towards my right, up. We'll draw it as up. Towards my left, down. Left, negative. Right means positive, towards my right. That is my convention. If you don't like this convention, you can use your own convention. So, anyhow, I am using that as viewed from the right hand bearing, looking from the top, towards my right, upward, towards my left, downward. Okay, now, so these are all, I think already we have found out these values because this is the total horizontal load at gear C, that is acting towards right. Towards right means up. Towards right means up, that is 3,476 Newton. Similarly, total horizontal load at pulley D, pulley C. Pulley C, this is C, this is D, this is D. Okay, so total horizontal load at pulley C is 4,878 Newton. That is also acting towards right. That is also up. So RAH and RBH, again I am assuming RAH and RBH towards my right, that is up. Now later we will see whether it is up or whether it is towards my right or towards my left. If it happens to act in the towards my left, in that case we'll change the direction. Now anyhow, for timing, let us assume it as towards my right. That means it is acting in the upper direction. So both RAH and RBH acting towards right. That is the assumption we have made here. So that is in the upper direction. Now taking moment as usual. Let us do this. So taking moment about B. So algebraic moment about B. Due to all the horizontal should be equal to 0. Clockwise positive. We take anti-clockwise negative as usual. Negative. Anti-clockwise negative. So RAH we already know that. So RAH into 1100. That is acting in the clockwise direction. It is acting in clockwise direction. So plus. Okay. Next again this is also acting in clockwise direction. Plus 3,476 into 500. That is also acting in the upper direction. What about this 4,878 about B is acting in the anti-clockwise direction. Minus 4,878 into 400 should be equal to 0. When I solve for RAH, I think I am getting around 85 Newton. That is acting in the upper direction. Now you please check it later at home. So anyhow, I hope you understood how to find out reactions here at the support. You apply the condition of equilibrium, take a moment about B. You can take moment about A also. There is no hard and fast rule. I have to take moment about B. Even you can take the moment about A. You have taken moment about B. So algebraic moment about B due to all the orthos should be equal to 0. Clockwise moment positive, anti-clockwise moment negative. What is moment due to RAH about B? The RAH into 1100. That already we know. What is moment? That is going in the clockwise direction. So plus. What is moment due to 3,476 about B? That's also going in clockwise direction. So plus 3,476 into 500. What is moment due to 4,876 about B? That is going in anti-clockwise direction. Minus 4,878 into 400. If you solve for RAH, it is plus 85 Newton. Now you apply the condition for force equilibrium. Algebraic sum of the horizontal forces should be equal to 0. Again, up positive as usual, down negative. So in that case, RAH plus RBH, all are up here. All are up. 3,476 plus 3,476 plus 4,878 should be equal to 0. If I solve for RBH, I think I am getting a negative value here. It is 8,000 minus 8,139 Newton. Now please see here, the direction will change. Whatever the direction I have assumed initially is not correct. Instead of acting in the upper direction, or instead of acting towards right, it is acting towards my left. That is acting in the downward direction. So RBH, that's what I have shown in the dotted line here. Dotted line RBH. Minus, that is minus 8,139 Newton, that is acting in the downward direction. I hope it is clear to all of you. So RAH is plus 85 Newton and RBH I am getting negative here. Okay, so initially, but I had assumed initially in the upper direction or assumed the RBH towards my right, but actually it is not acting towards my right, it is acting towards my left. So that's what minus 8139 Newton. Next we will draw the horizontal bending moment diagram. Okay. Now let us draw the horizontal bending moment diagram. For that, let us find out bending moment at each loading point. As usual, at the extreme end, extreme points, at the extreme point, bending moment MAH and MCH should be equal to 0. We know that bending moment at the end point will always be 0. So MAH is equal to MCH equal to 0. MBH. What is MBH? In the same manner, I can find out bending moment at point B, either taking moment due to all the forces to the right of point B or to the left of point B, because there is only one force to the left, to the right of point B. So what is that moment here? 4,878 into 400. So that is okay. Oh, what is that? It is sagging. Sagging. So bracket is sagging. How much is that? Sagging, 1 minute. What is the value? Let me check it. It is here. It is sagging. 1.83. 1.83 into 10 raised to 6 Newton millimeter. Similarly, what about bending moment at point D, MDH? Again, in the same way we can argue. I can find out bending moment at point D by taking moment due to all the forces either to the right of point D or to the left of point D. Because there is only one force to the left of point D, we can take bending moment due to RAH here. RAH into how much? 600. That is 85 into 600. Very small value. I think I will get here 85. That is around 0.0. Very small. 0.051 into 10 raised to 6 Newton millimeter. 0.051 into 10 raised to 6 Newton millimeter. Of course, it's also sagging. It is also sagging because it's actually the upper direction. It is going to bend in the like this. So the shaft is going to bend like this. Here also at point C, the shaft is going to bend like this. At point B, at point B, it's going to bend like this. Sagging. Both are sagging. I hope it is clear to all of you. So at point A and at point D, bending moment is 0.0151 into 10 to 6. That is sagging. Similarly, at point B, it is 1.83 into 10 to 6. That's also sagging. Both are sagging here. Both are sagging. Now, as usual, we will draw the bending moment diagram, horizontal bending moment diagram. Horizontal bending moment diagram. When we draw the horizontal bending moment diagram, let us draw that horizontal bending moment diagram. Horizontal HBMD. We call it as HBMD. End point, it is 0. Here it is a very small value, around 0.051 into 10 raised to 6. Of course, both are sagging here. Both are sagging. Of course, at point B, how much? 1.83 into 10 raised to 6 Newton millimeter. So just we will show this here. It will go like this, I think. So this is the horizontal bending moment diagram. Of course, these things are there. I will send this course material later. So it is there. Horizontal bending moment diagram. So, okay. So I think it is correct. Horizontal bending moment diagram because both are sagging. Now please remember, sagging I am taking it as positive. Hogging is negative. Now according to me, same convention, sagging positive, hogging negative. So that's why I have shown above the 0 reference line. Sagging I have shown above the 0 reference line. If it is hogging, I will show below the 0 reference line. Okay, next let us, okay, I hope it is clear. So now let us find out the resultant bending moment at each point because we know the bending, so we know the bending moment at each loading point due to vertical loading diagram and loads and horizontal loads already we know. So now let us find out the resultant. Of course, MA is equal to MC equal to 0, MD, MBV, MB square root of MBV square plus MBH square. Please do all these things. I don't have time here. So anyhow, please do this calculations because all values are available already. All these values are available here. Now just to substitute, I think MB I am getting around 4 into 10 raised to 6 Newton millimeter, and MD similarly MD. What is MD? Square root of MDV square plus MDH square. If I do that, I am getting 0.792 into 10 raised to 6 Newton millimeter. Okay, so which is maximum here? Bending moment at point B is maximum because bending moment at point is around 4 into 10 raised to 6 Newton millimeter, whereas at bending moment at point is only 0.79 into 10 raised to 6 Newton millimeter. Okay. Now, so maximum bending moment occurs at point B. So maximum bending moment occurs at point B. Maximum bending moment occurs at B. How much is that? M is equal to MB is equal to 4 into 10 raised to 6 Newton millimeter. Once I find out maximum bending moment, this is M only. Now let us find out equivalent twisting moment. This already we know. What is the equivalent twisting moment? Square root of Cm into M the whole square plus Ct into T the whole square. We already know T, we already know M, both are known. You just we have, please take Cm is equal to around 2, Ct is equal to 1.5. Please, these are all assumed value because otherwise it is available in the table. I think table 3.2 or 3.1. It is given for steady load or suddenly applied load with minor shock and major shock. Okay, please refer to the table. Okay, you please take the values of Cm and C because I have assumed Cm equal to 2 here and Ct is equal to 1.5. You please solve for Te. When I solve for E, please do these calculations there because all these values are away. Because I know M, 4 into 10 raised to 6 Newton millimeter. I know T also, that is 955. Torque is known. Already we know torque. So 955 into 10 raised to 3 Newton millimeter. This is already known. T is known, M is known, Cm and Ct. Just to substitute, we can get 8.127 into 10 raised to 6 Newton millimeter. 8.126 into 10 Newton millimeter. Now let us find out. Okay. Now I think this portion we can wipe now. This is not required now. So this is no longer required for us. All these things, we already know this. Now we will come to the last part of the design. What is that? We have to find out maximum shear stress. What is tau max? 16 Te by d cube. Because we are using solid shaft here. Please note, because we are designing solid shaft, it is 16 Te by pi d cube. In case if we are designing hollow shaft, it will be 16 Te by pi d naught cube into 1 minus k to the power of 4. So that type of problem also we have solved. So in the class, regular class, we have already solved all these things, all these types of problems. So if it is hollow shaft, it is 16 Te by pi d naught cube into 1 minus k to the power 4. What is k there? Diameter ratio. It will be given normally 0.5 or something. If it is not given, you please assume it. Now, for safe design, you apply, what is the theory? You have to apply maximum shear stress theory. So if you solve for that 16 Te, I think I will get 16 into 8.127 into 10 raised to 6 by pi d cube. I think if I solve for that, 41.39 into 10 raised to 6 by d cube Newton per mm square. And all those things we can do. Now, for safe design, tau max should be less than or equal to tau label. What is tau label here? What is tau label? Because in this particular problem, I think, because this is the worksheet problem, I will go to share that worksheet problem with you later. In that worksheet problem, I have given material C40 steel. C40 steel. Now, please refer to the table number 1.9. You all know that. You please refer to the table. You find out what is sigma y. I think it is around 324 Newton per mm square. Factor safety, I think that if it is not given, we will assume it. So in that case, I think in this problem I have given 2.5 or something I have given. So what is tau y? Tau y is equal to sigma y by 2. 0.5. That is tau is equal to, because we already know that for combined shear, the yield stress in shear is around 0.5 times the yield stress in tension. So sigma y by 2 is 0.5 times sigma y. 0.5 times sigma y. So if I calculate the tau y, I think tau y will get it as around 162 Newton per mm square. If I solve for tau label means what? Tau y by n. So tau label, I think if I solve for tau y by n, 1 minute over. Sorry. Tau label, I think I am getting 64.8. 64.8 Newton per mm square. Now you just substitute here 41.39 into 10 raised to 6 by d cube should be less than or equal to around 64.8 Newton per mm square. If I solve for d, I think I am getting around, how much is that? 86 millimeter. 86 millimeter, I am going to get the diameter of the shaft. No, this is one way of finding out the diameter of the shaft. No, there is another way using ASME code. Even we can use ASME code for this problem. In that case, I must know ultimate stress. For the same material, ultimate stress is approximately around 600 Newton per mm square. 600 Newton per mm square. No, that method also we can use. You see, there are two ways of designing the shaft here in this particular problem. Suppose if ASME code is given, you have to use ASME code. Suppose if I ask use ASME code design the shaft, you have to use the ASME code only. In case if I have not given, if I have not asked you to use ASME code, in that case I will give you this factor of safety, say 2.5 or 3, something like that. I will give suitable material for the shaft. All those things I will give. If not, we have to use ASME code. In case if I use ASME code, we need the sigma u. Ultimate stress also we need. So we know yield stress how much? 324 Newton per mm square. According to ASME code, tau label how much? 0.3 times sigma u or 0.18 times sigma y. Whichever is lower. Whichever is lower. Whichever is lower. This is without keyway. This is without keyway. Without keyway. So with keyway, no, that should be reduced by reduce it by 25%. reduce it by 25%. That's what, 25%. That is, tau label now actually will be equal to 0.75 in this particular problem. I think if you do 0.3 times sigma u, it will be around 97 Newton per mm square. If I do 0.18 times sigma, 0.3 times sigma y, yield stress, this is 0.18 times sigma u. If I do that, around 108 Newton per mm square. So out of this 97 Newton per mm, that is smaller value. Now for that, if you multiply that by 97, around approximately, I am getting around 72 Newton per mm square. So now the value is slightly changed. If I do this method, I am getting tau label 64.8 Newton per mm square. Whereas if I use ASME code, if you use ASME code, in that case, tau label is 0.3 times. You know that for steel purchased under definite specification, allowable shear stress should be at 30% of the elastic limit, that is 0.3 times sigma y. In this case, it is 97 Newton per mm square, or it should not be over 18% of ultimate strength, that is 108 Newton per mm square. In this case, 97 is smaller than this. So let us adopt that. This is without keyway. With keyway, that has to be reduced by 25%. That is just multiply by 0.75. I am getting 72. So instead of putting 64.8 here, if I put 72, I think I will get very close to this 86 millimeter. Okay, is it clear? I hope you understood how to design shaft. Okay, so anyhow, I am going to share this problem with you later. Thank you.